Picture this. You're going for a walk down the street or through the park, and you see a lovely ramp, and you think to yourself, well, that is a lovely ramp. I wonder how inclined this ramp is, or at what degree this ramp is going up. Well, maybe you haven't had this thought, but if you ever have had this thought, this is a way that you could calculate the angle of a ramp or any other shape that is of a triangular shape, I guess. Anyway, so trigonometry for unknown angles is what we're doing in this one. Now, it's pretty straightforward, and this is a follow-on from what we've done with regular trigonometry. So what we're going to do is we're going to start off by looking at our trigonometric ratios again. So as we said in the last video, we always want to start off with this one, okay? So SOHCAHTOA, okay? Now you'll notice with this particular triangle, okay, we've got two sides that are labelled, and we've got an unknown angle this time, and our unknown angle is down here. Okay, but we're going to label our sides in relation to this angle. Okay, so let's do that. So we've got the side over here, which is our opposite, and we've got the side that's across from the right angle, or the longest side of the right angle triangle, which is our hypotenuse. Now, which of our trigonometric ratios uses the opposite and the hypotenuse? So looking back up here, it's the sine. So we're going to write out our formula. Sine theta is equal to opposite over hypotenuse. And we're going to substitute in what we know. Now we don't know what our angle is, so we're just going to call it theta, as it's already stated as theta in our formula. Okay. Now let's substitute some values in. Our opposite is 6, and our hypotenuse is 12. Okay, so we just put them in like that. Now finally, what we want to do is we want to move essentially the sine from the left-hand side to the right-hand side. Now in year 9 you would have done this already, but just as a reminder, okay, there's not actually a times in between this. What this is called a function. It's a trigonometric function. And what it's doing is it's applying the sine function onto the theta. And the way we're going to get rid of it is we're going to do the inverse of the sine. So we need to do the inverse sine to both sides, okay? Now the result of this will look like theta is equal to, and we're going to write sine on the left-hand side, except we're going to put a -1 up there, okay? And this button appears on your calculator as well. And we're going to make sure we put it in brackets as well. So theta is equal to the inverse sine of 6 on 12. So let's calculate what this is going to be. So shift and sine gives us a sine with our -1. We only use this for when we're doing angles. Okay, so regular sine for lengths, inverse sine for angles. 6 over 12, okay, close it off, and we get 30. So what that's saying is that this angle in here is equal to 30 degrees. Okay, pretty straightforward, I think. Now, this is the same regardless of what your triangle is, okay, and what triangle you're using. Okay, and it doesn't matter. It doesn't change. The method doesn't change using whatever ratio you're doing to, as long as you're using the right ratio. So to show you that this is the case, okay, what we're going to do is we're going to do another triangle. Okay, now this time we're going to do a triangle like this, and it's going to have a 2. It's going to have a, well, let's not say 2, let's go instead 3, 2, and say 4. Okay, so I don't actually know if that makes a right angle triangle. Probably not. In fact, let's just do the 2 and the 3. Okay, we'll ignore the other side. We could probably use Pythagoras to work out what that other side's going to be. Okay, but for now, we're just going to do this one. Now we need to put some angles into here that we can calculate. So I want to work out what both of these angles are. So let's put an alpha in this one, and we're going to put a beta in this one. Okay, so there's some Greek letters like theta, alpha, and beta. Okay, so let's start off by finding our alpha, our angle for alpha. Okay, so using our angle for alpha, okay, we're going to be using the opposite, and we're going to be using the adjacent. Okay, so in this case, it's opposite and adjacent. So the one that uses opposite and adjacent, if we go back up and have a look, is the tan ratio. Okay, so tan theta, and we're just writing out the ratio this time before we substitute. Tan theta is equal to opposite on adjacent. Okay. Now we don't know what our angle is, but it's being represented by a different Greek letter. So we're going to write in tan alpha. Okay. So alpha is our Greek letter of choice. Our opposite is 2, and our adjacent is 3. Okay. So to finish this question off, we're going to do the inverse tan of both sides. So that's where we put the -1 up here. 2 over 3. We're going to plug this into our calculator. 2 over 3. Close it off. Hit equals. And we get that alpha is approximately equal to 33.69 degrees. Or if we wanted to put it in minutes, degrees, minutes, and seconds, we just hit the degrees, minutes, and seconds button. And we get 33 degrees and 41 minutes if I round it to the nearest minute. Remembering that to round to the nearest minute, it's to the nearest 30 seconds. So if it's above 30, then it goes up. And if it's below 30, or 30 and above, it goes up. And below 30, it will go down. So if this number is above 30, then it would go 42. If it's below 30, it would stay at 41. Okay, now let's do the same thing, but for the beta. Okay. So let's write out my formula. It's going to be another tan one because we've got an opposite and adjacent. The opposite this time is the 3, whereas the adjacent this time is the 2. Okay. So let's put my letters in, O and A. Okay. And so remember, it's always based on the angle that you're picking. So the angle that we are picking is the beta angle for this second one. So tan of beta is equal to the opposite, which is 3, over the adjacent, which is 2. Okay. Now you're doing the inverse tan. We get tan -1, or inverse tan of 3 over 2, or 1/2, 1.5. So beta is equal to, so all I've got to do is just swap the position of the 3 and the 2 around. We get 56.31, or 56 degrees and 18 minutes, like that. Okay, pretty straightforward. And that's pretty much all that you guys need to know. Now, as a little bit of an extension one, okay, this is just doing another problem, but it's another one that we can have a look at. Okay, that just looks at 2 of the ratios and a cool little consequence of the ratios themselves. So let's make this a actual triangle that I know exists, a right angle triangle that exists. So a 3, 4, 5 triangle. Okay. And what I want you to do, or what I want us to do, is I want to we're going to do the same thing. We're going to do alpha and beta. Okay, we'll put alpha up here, we'll put beta down here. And I want you to work out the sine and cosine of both alpha and beta. So pause the video and have a go yourself. Okay, so this is number 3. Have a go at yourself, finding the sine and cosine of both alpha and beta. Okay, or sorry, finding the angles of alpha and beta using both sine and cosine. Okay. All right, so to do so, what we're going to do, sine alpha is equal to, and of course you could use tan as well, but I want to use sine and cosine for these ones because I want to show you guys something. Okay, so we're going to go sine alpha, so opposite on hypotenuse. So sine alpha is equal to 4 on 5. Okay, so alpha is equal to the inverse sine of 4 on 5. Okay, and so alpha is going to be equal to, so 4 on 5, which is equal to, and we'll call it 53.13 degrees. Okay, to 2 decimal places. Now we'll do the cosine of alpha, okay? So watch what happens with the cosine of alpha now. Ready? So the cosine of alpha, we need the adjacent and the hypotenuse. Alright, so the adjacent and the hypotenuse, so my adjacent is 3, my hypotenuse is 5. So it's equal to 3 over 5. So alpha is equal to the inverse cosine of 3 on 5. So alpha is equal to, and I hope you guys could probably guess what this is going to be equal to. Okay, but let's put it in, 3 over 5. And it's also equal to 53.13 degrees. Now, does that make sense in your mind? Have a think about it. Well, we're doing the same angle, okay? Now, if we were to do a calculation where we're trying to find the same angle, but doing it two different ways, surely we should come up with the same solution because we're trying to find the exact same thing. We're just doing two different methods. And that's the point in this case. The point is, it doesn't matter which method you use. You could use sine or cosine, or you could use tan. In fact, if you did use tan, and I'll quickly do it on the calculator, shift tan of opposite over adjacent, so 4 on 3, you're going to get the same answer every single time because the ratios stay the same, okay? Because the angle that you're using, well, it has to be the same size, okay? Because if it was changing depending on the ratio that you would have, or that you're using, well, that would mean that the triangle is changing sides every time you're doing it. It's the angle itself is just moving around, and that doesn't make sense. All right, doing the same thing for beta now. Let's do it in purple. So sine beta, and let's have a look and see what happens with the sine beta. You may have noticed this with the tan ones before, but we're going to do the same thing. So sine beta, okay, so that's the opposite over adjacent. So let me get rid of the red markings, and I'm going to replace them with the blue, the purple markings. So the hypotenuse stays the same. The opposite from the beta is over here, and the adjacent of the beta is this one down here. So sine is opposite over adjacent, opposite over hypotenuse. So it's 3 on 5. So beta is going to be equal to the inverse sine, 3 on 5. So beta is going to be equal to, let's put it in, and I'm hoping you guys are going to guess what this one's going to be. And you should be able to work it out even without having to do trig, because it is a triangle, and we know it has to add up to 180, and we know that one corner is 90, and the other corner is 53.13. The other one is 36.87 degrees, okay? So what do you notice about these two here? I'm hoping you notice that when you add these two up, it adds up to 90 degrees. Okay, so, and to test that, just to double check, to make sure I'm not mucking around with you, 53.13 plus 36.87 is equal to 90. So those two sides, and we know they should add up to 90 degrees as well, because if you think about it, it's a right angle triangle, one of the corners is 90 degrees, so the other two must also add up to 90 degrees to make the 180. Okay, finally, the cosine of beta. Well, without having to do anything, we should be able to work out what this one's going to be. Okay, so substitute our values into the formula, rearrange by putting the inverse cosine on the right-hand side, put it into my calculator, 4 over 5, close it off, and we get the exact same value. Beta is equal to 36.87 degrees. Okay, so these are basically the methods that you guys need to follow for this lesson. Okay, so have a go at those, and there'll be a worksheet for you to have a go at on top of that. Ciao.